So thank you very much for joining the first session of the second day of Q Science Day. And it is my pleasure to introduce the first speaker, who is actually an invited speaker, Tracy Northup, and who is an Ingeborg Hochmar Chair of Experimental Physics in the University of Innsbruck, and is a leading authority using trapped ions for all kinds of quantum information processing purposes. And also the talk is about this. So thanks a lot for accepting our invitation, and please start your presentation. We are looking very much forward to it.
Thank you so much for the kind introduction. Let me just get back to the start here. Okay, and hide the pictures of the participants so I can see the slides. Okay, great. I hope you can see the slides and hear everything okay. If not, let me know.
Yes.
And thank you again for the really kind invitation. It's wonderful to be here, and great that you were able to put together these 2 days of talks this week. It's a really nice opportunity. So I'd like to tell you today about work that we're doing on constructing quantum networks based on trapped ion quantum computers. And so the starting point for this talk is the question, how can we connect different kinds of quantum systems? And this is the kind of device that maybe in the past year people haven't used so much, a travel adapter when you're going between countries. This is an example of kind of an artificial device that the reason we have to connect, have devices that help us link between different kinds of power is because we, as a society, different countries decided on their own rules for voltages and frequencies. So in some sense, this kind of a device in the picture is only necessary because, could have been avoided with some better coordination. But the question about connecting different kinds of systems, that's more fundamental. You can ask, do we really need to connect different kinds of quantum systems? And the answer is yes, we expect that we're always going to have to do that. It is a fundamental problem because we don't expect that a single quantum platform will be the solution for all of the quantum technologies that have been proposed in recent years. So I just wanted to show you some pictures to get started. Pictures that you may have seen before, even in the past few days. In Barry Sanders' talk yesterday, he was showing pictures of these superconducting qubits from IBM. And here I'm also showing you a picture of a string of trapped ions. We're looking at the fluorescence of those ions in an ion trap. So ions and superconducting qubits are two of the main candidates for quantum computation. But they're not the only candidates. There are many different experimental platforms that are under consideration for quantum computation. And then you might say, okay, well, maybe we'll figure out that there is one best quantum computing platform. That might be the case, but it's also quite likely that say for quantum simulation, that there's actually another platform that's more suitable. So here's an example of neutral atoms in this beautiful Eiffel Tower shape that are being kind of held in these arrays, and that are really well suited to have kind of large simulations based on arrays of hundreds or even thousands of atoms interacting with each other. And another application, quantum sensors, again, you might think of different requirements. For example, being able to bring a solid state device like a nitrogen vacancy sensor very close to, say, a biological sample in order to probe, say, the magnetic fields or electric fields. Quantum communication. So here, certainly photons, are what we all think of because they travel at the speed of light as quantum systems. So what I'm showing you is this range of experimental platforms, and we, anticipate that the landscape of quantum technologies is going to involve all of them. And moreover, we anticipate that we're going to want to connect these platforms to one another, that they're not going to simply operate independently, but that we're going to be able to enable fundamentally new capabilities if we can link between ions and photons, or maybe between ions and nitrogen vacancy centers with the help of photons. And, I probably don't need to tell anyone here that, it's an exciting time to be working on quantum science. People talk about a second quantum revolution. There are efforts worldwide that are underway to harness these, beautiful quantum and mysterious quantum effects of superposition and entanglement, or, strange quantum effects that are counterintuitive. So, here I'm just showing a picture from the Quantum Technologies timeline of the Quantum Manifesto, which is about this plan for Europe to really support and invest in quantum technologies. But as I'm sure you're aware, there are initiatives worldwide to do this. And I think also, we can think of these Q Science Days, this QWorld initiative as a really wonderful example of a way that of efforts to unite together these quantum research across different countries, which is what we're going to need to realize these kind of ambitious visions. I'm showing you different quantum technologies like sensing and simulation as a motivation, but and again, right, this is what I've pointed out, that in Europe, this manifesto fits into this quantum flagship program, which is a 10-year program for funding quantum systems. But what I want to emphasize also before I start my talk in depth is that this is not really just about technology. This is really fundamental science. And I would say that, when I think about why I'm interested in these interfaces between quantum systems, it's because they offer a window onto really fundamental interactions between light and matter. And I find it, as an experimentalist, really beautiful and exciting that we can look at these interactions, in the lab with things that we're able to build in these, experiments with just a few people working on them. Okay, so that brings me now to my outline. I hope I've tried to motivate the idea of these kind of quantum interfaces based on ion traps. And so I'd like to start by showing you a particular kind of quantum interface that we're working with and outline two main ingredients for these interfaces. And then I want to focus down on trapped ions for quantum networks and outline for you what's been done so far in this research area. And in the third part of my talk, I'm going to turn to our research here in Innsbruck and describe to you efforts to couple together two remote ion traps via optical cavities. So let me get started with this idea of a quantum interface. And here's a big picture vision, the idea of a quantum internet. So back to this idea of quantum technologies, we're interested in communication over long distances in this European-centered vision. This is across Europe. And this is a picture from an initiative that we are part of, which is called the Quantum Internet Alliance. It's supported by this quantum flagship program in Europe. And so in this vision, the idea is that you have, in such a network that's depicted here, you have quantum nodes where you would carry out local quantum computation as well as simulation and sensing. And those nodes are linked together, in the picture by these kind of glowing blue lines. What is that really supposed to indicate? It's supposed to indicate either free space channels or fiber optic channels that are linking together those nodes over distances that can really only be traversed with light. And so the idea is that we're going to need, over these quantum channels, we're going to need to distribute quantum states. And so when I'm talking about a quantum internet here, I'm talking about a most general version where our goal is to be able to distribute quantum states across such a network. So certainly there are tasks for quantum computation that require less or fewer resources. So if you can send, for example, even polarization states of single photons, you can already do, you can already distribute keys or establish secret keys between remote parties. Here, though, we want to kind of harness the full capabilities of quantum communication, and that's going to be about being able to distribute entangled states. So the question that I want to ask then is, how could we distribute entanglement efficiently and with high fidelity over long distances? That is, how can we really preserve this entangled nature? And so the two ingredients in the approach that we're using that I'm going to tell you about, the first of these ingredients is an ion trap. This is a picture, I think, from the German museum, the Deutsches Museum in Munich, about one of the very first ion traps that was built by Wolfgang Paul. And so you can kind of see that it's in a glass cell. It's comprised of several electrodes. This is also another picture of such a trap, quite similar probably in size, metal electrodes held together by insulators. And then kind of on the right-hand side, a more a modern version, but really all three of these are kind of doing the same kind of three-dimensional trapping in the same way. And now on the bottom, you start to get to sort of taking these three-dimensional ion traps to a chip scale. So you can actually map a three-dimensional trapping geometry onto a two-dimensional set of electrodes. And one advantage there is that you can use sort of several electrodes to sculpt the potential that's seen by the ions. So that's one example from Sandia, their high optical access 2 trap. Here's another example from NIST in Boulder, Colorado. This is actually a little example that we're working with here in Innsbruck. It's actually, it's kind of funny because it's a three-dimensional trap like the ones above, but it's kind of processed also on a chip. So it sort of has some features of both of these aspects. What I'm trying to show you on this slide very broadly is that ion traps can look very different, but there's a number of different approaches that you can use to use radio frequencies to trap these charged particles. Yeah, so the big picture here, we'll get into it in more detail, is that we want to use electromagnetic fields to confine charged particles. I'm going to focus here on Paul traps, and in particular on linear Paul traps. One can also use Penning traps, which are basically using magnetic fields to confine charged particles. But for quantum information processing, most of the work, though not all of it, is being done with Paul traps. So that's the first ingredient. And the second ingredient today is going to be optical cavities. So we can think of an optical cavity here as something that we're using to trap a light field, just like we're going to use electromagnetic fields to trap ions. And so we can trap a light field by putting two mirrors opposite to one another. So if we have highly reflective mirrors, then a single photon will bounce back and forth between these mirrors hundreds of thousands of times before it escapes. What does it mean to escape? It means that one of those mirrors has, or both of them have, some small probability for transmission. And so the photon will leave in a well-defined mode, which we could then send to another system or in fact detect. And so this allows us to confine the interaction between the electric field of an ion so the electric field of the light field, sorry, and a particle, that is, of an ion, that the electric dipole of an ion, to a very small mode volume. So let me just show you a couple of experimental examples. Of course, the beautiful experiments from Serge Haroche's group leading up to his Nobel Prize work with microwaves interacting with Rydberg atoms. So here you see one of the seminal experiments from the Haroche group where Rydberg atoms crossed microwave cavities. And also from again, more than 2 decades ago, work in Jeff Kimball's group on optical fields interacting with atoms. So here, in these first experiments, this was looking at atoms crossing through optical cavities. And then later on in later work, there's been work actually in both of these cases, it's Rydberg atoms and optical fields with neutral atoms crossing through cavities. And in later work, those atoms or ions have been confined inside of cavities. So I've been talking about atoms here, but this principle of coupling together a 2-level system, a matter-based quantum bit with an optical cavity for light storage can of course be extended to solid state systems, including but not limited to superconducting qubits coupled to microwave resonators, as well as nitrogen vacancy centers or any other kind of diamond defects, or quantum dots also coupled to optical resonators in that case. So those are the 2 ingredients that I'd like you to think of moving forward. And now I'm going to outline what's been done so far in terms of applying these trapped ion experiments to quantum networks. Okay, so let me just remind you of this big picture where we want to link together quantum nodes. And now that we have this picture of ions being trapped in these electromagnetic fields in a linear Paul trap, you should picture these Paul traps at each node. And so what I want to tell you here is that these trapped ions have really promising characteristics for networks. This is now a picture also of one of these linear Paul traps, but you're sort of seeing it in its native environment in a vacuum chamber. So we're kind of looking through with this nice camera angle into a vacuum chamber. And then we see that there's light scattering off a Paul trap inside. So the vacuum chamber is necessary because we want to minimize collisions between the ions that we're going to use for information processing and storage. We want to minimize the chance that those ions collide with gases in the background, in background gas, so which would then create molecules. So you wouldn't have the ion anymore that you were trying to work with. Okay, and now looking more deeply at this concept of a Paul trap, you can think about, here's a picture where you have 4 gray electrodes, and we'll talk about applying radio frequency to all 4 electrodes, but typically what's often done in experiments is to ground 2 electrodes, as I've indicated here, and to apply a radio frequency voltage to the other 2. And so those 2 are in phase and the other ones are grounded, although you can apply opposite phases as well. Okay, and so by applying the radio frequency voltage, that's going to provide a radio frequency pseudo potential in 2 dimensions. And then in the 3rd dimension, we apply DC voltages to provide a 3rd confining potential. So yeah, as you may recall from Earnshaw's theorem, from electromagnetism, we aren't able to use electric fields to provide a 3D trapping potential, but we get around it with this idea of a pseudo potential. So essentially you can think of it like a saddle potential that's rotating so fast that the ion can't keep up. And so it doesn't escape. And this traps then, once we have the ions confined there, that allows us to coherently manipulate their electronic and motional degrees of freedom, either with lasers or with microwaves or with both. So in the work I'll tell you about today, we're using lasers, but there are other research groups that have achieved really exciting results with microwave manipulation. So this little cartoon of a harmonic oscillator is to remind you that what the ions are going to see is a potential well, in this case in all 3 directions. So you can imagine a tensor product space. So there's essentially you can think of it as 3 independent harmonic oscillators for the ion. The traps for these ions are about 10 electron volts deep, so much deeper than thermal photons, which is why it's fine to do these experiments not in a cryostat at room temperature. And in fact, the ions are trapped for days, or even depending on the species and the background conditions for weeks or months in such a deep trap. And the oscillation with which the frequency with which the particle is rolling around in the trap is on the scale of megahertz. So again, here's the picture that I showed you before, now a bigger version, looking at what these crystals of ions look like in the trap. So why would you form a crystal? Well, you have ions along the trap axis, so they're being confined in orthogonal to that axis by the 2-dimensional pseudopotential. And if you relax the trap a bit more along the 3rd axis, then they will kind of preferentially line up along that axis. So on one hand, they see a harmonic potential, but on the other hand, you have Coulomb repulsion, and that gives you a characteristic spacing here, which is on the order of about 5 microns. So this is a picture from Rainer Blatt's group where they've worked with these beautiful long strings of ions. The work that I'm going to tell you about today is with just a couple of ions, but certainly the fact that you can use these long strings, not only trap so many ions, but also individually manipulate them with lasers or microwaves and store information there as well for long times. That's really one of the strengths for computing platforms. Here, what you see are also from Rainer Blatt's group 2 images looking at the shared motional modes. So on one hand, on the left-hand side, we have a center of mass mode of this crystal of ions, and on the right-hand side, a stretch mode. So these are just the ions that are in the as coupled oscillators seeing this shared potential. And so these are the modes that we take advantage of in order to perform gate operations on the ions. That is, we take advantage of the fact that we can couple the electronic structure of the ions to the shared motion in the trap potential. So that's a picture of ions in a single trap. And then the question to look at today is, how can we build links between ions in distant traps? So now this is the picture I want to have you to have in mind of 2 Paul traps separated by some distance. And I've sketched sort of a little orange wiggle here to show you, an optical fiber connection that would link those 2 systems. So now in this case, we're not going to be able to rely on shared motional modes for gate operations. And so I want to tell you a bit about how you can then link the states of the electronic states of ions in two different traps. And that's work that was really pioneered by Chris Monroe's group, formerly at the University of Maryland and JQI, now at Duke University. So starting with work now back in 2004 by Boris Blinoff and colleagues, where they first entangled ions with optical photons, and then they continued to do a number of experiments generating remote entanglement between ions. So I'd like to step you through the key concept there using this image from the third paper that I've listed, the 2015 Nature Physics paper, which was kind of the most recent version of that experiment. So here's the concept. You should picture that there's two ion traps, and this is a picture from the Monroe group of the kind of traps that they're using. Again, it looks kind of like that zoo of traps, one of those things from the zoo of traps that I showed you earlier. And then you can picture that in one of the traps, there are two ions, and then the third trap, there's just one. So these are the ones that are labeled A and B. And the key is, the first step is to entangle each of two ions with a photon. And that entanglement happens via spontaneous decay. So to be more precise here, we're entangling the polarization degree of freedom of the photon, of a single photon, with the electronic state of the ion. And this is a sketch, again, used from the using ytterbium-171 from this Monroe paper, where the ion is first excited with a short pulse to the p1/2 state of ytterbium-171. And there's two different decay channels with two different polarizations. So you can see that that's going to produce an entangled state where either the ion is on the left-hand side in the -1 state, and it generates a sigma plus polarized photon, or it's on the right-hand side generating a sigma minus polarized photon. So what do you do with ion photon entanglement? Well, you collect those photons, and that's the lens, those two lenses that you see. Each trap has its own lens for collection. The photons are then coupled into optical fiber and sent to a beam splitter. And the beam splitter is going to erase the information about which path each photon came from. So now if I detect a photon at either one of the beam splitter outputs, I'm not able to say which trap it came from originally. And then the final step here is photon detection. And so ideally now, if you've generated two photons, each entangled with one of the atoms, then you're also going to detect two. Certainly there will be plenty of times when you don't because of losses in the channel, but then you can ignore those cases and focus on the events that are detected. So you're going to get two detection clicks at one of these photomultiplier tubes in the sketch, and that detection event projects the ions into an entangled state. So not every detection event, but certain detection events which because of this indistinguishability, because you've erased the information about which path the photon followed, that then prepares entanglement between the two ions. So I want to summarize again with this slide what's been achieved so far. This method is able to prepare very high fidelity states, first of ions and photons entangled with each other, and then going on further with the two remote setups. In the picture I just showed you, they were kind of meters apart, these two vacuum chambers. It prepares also high fidelity ion-ion entangled states, and at a rate of about one entanglement event every 0.2 seconds, so about 4 or 5 events every second. And what was really exciting about the most recent result now from about 5 years ago is this coherence time of more than a second. So it means that you can, while you're doing this, you can also store information in these ions for longer times than it takes you to generate entanglement with a remote ion. And that was the first demonstration experimentally of remote entanglement being achieved faster than decoherence. The reason I'm highlighting this is now if you want to scale this proof of principle experiment up to more systems, you can imagine that it only makes sense to do that scaling if you can kind of build faster than everything falls apart, right? So if your network is falling apart faster than you can build, it's not going to be useful. But as long as you can hold on to coherence, then it makes sense to build more and more complex network connections. So that was with a particular ion species, ytterbium. The photons were in the ultraviolet or blue, and there's been more recent work from an Oxford ion trapping group, which has really pushed these fidelities, both for ion photon entanglement and ion entanglement, really, significantly upwards, and also achieve faster rates by using strontium ions. And so I think both of these results are really extremely promising for work to show that you can link together two remote ion traps. So what I've showed you is based on spontaneous emission from an excited state. And now I want to shift gears and tell you about our research. And we're going to start that by asking the question, instead of basing this interface on spontaneous emission, can we construct a coherent ion photon interface? So this brings me to the third part of my talk, where I'd like to tell you about our work on coupling two remote ion traps, each coupled to an optical cavity. And here's a system that's been the workhorse in my group for some time. This is, it actually predates my group. It was a system that was built up several years ago in Rainer Blatt's group. And it's an ion trap in the middle. Hopefully you recognize it from the picture before. It's now rotated by 90 degrees from this image I've shown you before, but now hopefully you can see two of the four blades that provide a radio frequency potential for that two-dimensional pseudopotential confinement. And then these kind of pointy electrodes that are a bit shinier above and below, and that's providing the DC confinement. So we're typically putting voltages on the DC electrodes of something like 1,000 volts, and on the RF electrodes, also kind of amplitudes on the scale of 1,000 volts and frequencies of kind of 23 megahertz in this case. Okay, so that's the ion trap, and now the cavity. You can see these kind of metal circular shapes which are holding highly reflective mirrors. Those are 2 centimeters apart, and what you should picture here is an optical mode between those two mirrors, like the one that's sketched above. And in the sketch on the left-hand side, you see a little green dot, and so that's where you should picture kind of an ion trapped in the middle of this ion trap. Okay, so this is a picture of a setup that allows us to put a single ion in a cavity, and that really brings us back to proposals. This is a paper by Jeff Kimball about the quantum internet, outlining the idea of coupling together ions or atoms. In this paper, it was a focus on really actually any two-level system, how you could couple together such an emitter with an equivalent remote system, again, by coupling it to a cavity field and then watching photons leak out of that field. That's what you see in this kind of red temporal wave packet that's labeled kappa, which is describing the decay of the cavity. And that photon is then sent to a remote cavity system. So this is very much in the spirit of that paper. Now what I want to show you is the physics of that interaction between the ion and the cavity field. So here I've taken away most of the blades of the ion trap and just the two end electrodes here to make things a little simpler. And we're going to look at these mirrors, and we have this picture of a standing wave field in between the mirrors. What I want you actually to remember, though, is we're actually not going to drive the cavity with a laser field. We're going to use the vacuum field here. So here, what we're going to do, I'm showing you the simplest possible kind of atomic structure where we can think of 3 levels. A ground state, which is called S, and an excited state, which is a P state, and a D state, it's a metastable state. You can think of it as a ground state. So it has a lifetime of about a second in this system. And this is a system is calcium, it's calcium 40. And hopefully I'll tell you in the next few slides about some reasons why it can be particularly suited for these experiments. So what I sketched here with 2 arrows is a Raman process, which is, you may remember from atomic physics, is going to allow us, if we use 2 laser fields, it would allow us to couple together 2 ground states without populating an excited state. Here, instead of using 2 laser fields, we're going to replace 1 laser field with the cavity, and in fact, with the cavity vacuum field. So in that case, we can still drive a Raman process. It turns out that if we have just 1 laser, and that's what's indicated on the left, together with this vacuum field, but we adjust their frequencies correctly, we can use it to transfer an ion from one state to the other state to the right-hand side, avoiding population of the excited state. And in the process, we generate a single photon in the cavity to make up for that energy difference. So that's going to go, that unitary evolution of that system will take us back and forth between the 2 states, absorbing and re-emitting the photon. But eventually that photon is going to leave the cavity. And when it does, the ion will also be stuck over here in the right-hand side until that state decays about a second later. So this is a really nice process to generate a single photon, just one. And we can also tell which state we're in by looking at atomic fluorescence. So this is a case where I've now introduced another state on the left-hand side that's labeled P1/2. And if we drive fluorescence to that state, we're only going to see fluorescence if we're in the S1/2 state, but we won't see fluorescence of the ion. Will be dark if we're in the D5/2 state. Finally, we have the capability to coherently manipulate the population in those two ground states directly via a laser that couples the quadrupole transition. So those are the ingredients we need now for this, for understanding the atomic physics that links together the ions and photons here. And now I'm going to outline for you how we can entangle the ions and the photons. So what I've shown you is how we make a single photon. Now what we're going to do is entangle them, and we're going to do that with two parallel processes. So essentially, we're going to introduce a second metastable state on the right-hand side. So now I have two states that I've labeled D and D prime. And that's because in this D5/2 state, it's actually a manifold with 6 different Zeeman states. So I have the freedom to pick out 2 of those states. And now what I can do here is use a laser, actually. So here, going back one step, I use a single laser field to generate one photon. I can use a second laser field to generate a second photon. The reason I have to use 2 fields is because there's a slight energy difference between the 2 final states because of the magnetic field that we've applied to split the states out. So I generate 2 different photons. The photons have the same frequency, which is determined by the cavity. And I choose 2 states so that the photons are prepared in orthogonal polarizations. So we refer to this as a bichromatic Raman field because the Raman field, the blue laser field, has 2 different laser frequencies. The photons coming out here have 2 polarizations. And so it means if I started with my ion in the S state, I can now have 2 possibilities. I can either generate the ion in the state D with a horizontally polarized photon, or the ion in the state D prime with a vertically polarized photon. And when I drive those processes in parallel, I generate the sum of the 2 states. So both states are equally probable. And the key aspect is that because this is a coherent process, there's a phase relationship between the 2 processes. And so it really is an entangled state, and in fact, a maximally entangled state. So this is work that we did several years ago, characterizing the entangled state. We can measure the ion and the photons in order to map out a density matrix that describes the joint state of the ions and photons, and we can verify that they're highly entangled with one another. And we can also show that we can vary the different phases of that entanglement as well as the amplitudes. And that's a real advantage of using this kind of a coherent process in contrast to the spontaneous emission process that I told you about earlier. So in fact, the tunable amplitude and phase is one advantage. Another advantage is we can tune the temporal wave packet that's emitted by the cavity with which the photon leaves. So that's kind of wave packet that I showed you in the picture, linking in the proposal to link together remote systems. And finally, of course, because the cavity mode is well defined, the photon doesn't get emitted into 4 pi of free space. It gets emitted into a well-defined mode. So I said here near unit efficiency, right? I can show you a little more about that on the next slide. First, I want to show you that some work that we did. So to start out with, we had just one cavity, but we could still entangle 2 ions with each other by entangling each of 2 ions in the single cavity with a photon. And then, just as in the experiments I've shown you from the Monroe group and talked about also from the Lucas group at Oxford, we took those 2 photons, we measured them, and with the measurements on the photon, in this case, we did something called a parity measurement, looking at whether both photons were, we measured the ions so we measured the photons in particular polarizations. That'll then, to verify the entanglement, we measured the ions, seeing if they were both in the same state, which would be a parity that's even, or both in opposite states, which would be odd, and seeing how that parity evolved as a result of rotations on the ion state. And that allows us to verify the entanglement and to show that they were also highly entangled through this process. I want to show you actually some most recent work that we've done in this direction. So this is an article that actually came out yesterday in Physical Review X Quantum. And so this is about showing that that interface between an ion and a photon is really achieved with near optimal efficiency. And this is work that was carried out in Ben Lanian's research group here in Innsbruck. And so it's looking at these wave packets. What you see above here is these different temporal shapes of photons coming out of a cavity. The reason there's 3 different ones is because we're driving the photon, or we're driving the Raman process with 3 different intensities. So the gray one is with the highest intensity field, so the photon leaves faster. The blue one was with the slowest field, so the photon takes more time to come out. And what you see in the inset here is that looking as a function of time and looking at the total probability to collect a photon, this saturates a bound. So first of all, you come kind of close to 50% detection rate in terms of these photons that are coming out. And then when you calculate actually an analytic bound that was proposed by Takao Aoki's group in Japan and at Waseda University, so they've shown that actually you can show that this kind of cavity system has a maximum efficiency, and this is a system that really saturates that bound. So yeah, below I simply sketched the system that's used, again, to remind you that there's an ion and a trap, and a drive laser generates a photon. The photon comes out and is detected. And then also in this recent work, this is a picture of data showing trains of photons. So a series of photons being demonstrated or generated at a single cavity, one after the other. That's the top picture. And the lower images are showing you kind of the probability to detect increasing number, or the second one is showing you another wave packet, the temporal shape. The third picture is showing you the probability to detect an increasing number of photons in a row. And so these kind of trains of photons could be a resource for cluster states. So these are just single photons here, but if you combine this with manipulation of the ions, you can use it to kind of generate entanglement between sequential photons in a resource that could be potentially used for quantum computation. Okay, so everything I've told you up to this point has been about a single ion in a single cavity, or I briefly told you about 2 ions, but everything was in a single cavity. And now I want to move towards entangling remote cavity coupled ions. So the photo I showed you above on the left-hand side, this is from my research group. This is the building I'm talking to you from today at the University of Innsbruck. So I'm here at the 4th floor, looking out towards the north, which is where those mountains are in the picture. But here's another building on our campus. It's about 400 meters away. And in my colleague Ben Lanian's research group there, he and his team have a similar system, sort of a newer version of this cavity coupled ion trap. And we have the good fortune to have an optical fiber that links those 2 experiments. So, right, we want to now take advantage of that fiber link and entangle ions in those 2 traps. How do we do it? Well, we're going to need to use the same approach, or one approach is to use the same approach I've told you before, entangle each ion with a photon, measure the photons. And a key requirement here is that those photons are indistinguishable. So recall that, I said that beam splitter could erase the information about where the photons came from, but we need to do more than erase the information about where. It also needs to be true that spectrally and temporally those photons can't be distinguished. And that was kind of a given with the spontaneous emission from the atoms. But now things get a little bit more complicated with the optical cavity, because that might let us make a distinction between these 2 systems. So, right, we can verify indistinguishability via what's known as the Hange-Mendel effect. That is, if photons are truly indistinguishable, Hange-Mendel effect tells us that they will leave a beam splitter at the same port. And so we will never observe coincidences from 2 photons at opposite ports that were really indistinguishable, sorry. So we've tested that first with photons from the same cavity. So here we're focusing now on the system on the lower right-hand side, and we use it to generate a train of 2 photons. So the first photon, so this is again work done in Ben Lanian's team, the first photon is generated and then time delayed so that it actually arrives at the beam splitter at the same time as the second photon. And we use that to say, to help us analyze, are these really indistinguishable? The reason we need to compare them, again, it's because of the cavity and because of, in fact, the Raman process, which is not perfect. It may sometimes give us spontaneous emission that could destroy the coherence of the process. So, right, as I've written here, spontaneous emission during this Raman process in the cavity will compromise indistinguishability. Here's some kind of theoretical study done in Nicolas Anguar's group, in particular by Pavel Sakatsky, looking at the photon probability. And so what you see in the dashed lines are kind of the pure case, a transform limited pulse that wouldn't be affected by spontaneous emission. And then the solid lines, sort of the case with everything included, that which shows, kind of gives you a sense of the contribution of spontaneous emission to this process. So it is certainly playing a role. We wanted to understand how it compromises indistinguishability, right? So you see actual and transform limited in these two cases. And now this is data, again, from the Lenin group, looking at what you see in red is the model from Nicolas Anguar's theory group, and black data, first looking at sort of degeneration of just a single photon. That's what I showed you before, the temporal wave packet. And in the second plot, what we see is now the coincidence probability. So in the case that's green, we actually don't have the photons arrive at the same time. We on purpose impose a delay. And so it then in that case, when they're clear, we've clearly on purpose made them distinguishable, there is a non-zero probability for them to arrive at the same time in the middle at detection time tau, t equals 0 or tau equals 0. But in the blue case, when they're really coincident, we see this dip, which is the so-called Hong-Mendel dip, go all the way to 0. And that's verifying for us that we really do have indistinguishable photons. So we found that very encouraging from a single system. And that lets us now move ahead and say we'd like to entangle two remote cavity coupled ions. So we introduced the second system again, our system over here at the university. And we are sending now together two photons just to check. We're not yet entangling them. We're just checking that they're really indistinguishable. And this is what you see here in the plot that I'm showing on the upper right-hand side. Again, we introduce a time delay, in which case we do see coincidence. But when we really have the photons arrive at the same time, this dip, this probability for them to arrive at the same time goes to 0. So that was kind of laying the foundation for entanglement. What we've observed here, the data I'm showing you is this Hong-Mendel interference. And what we've been really focusing on these past few months is taking data on remote ion-ion entanglement. We have some really nice preliminary data. We're analyzing it now, so it's a very exciting time here. I don't have anything to show you yet that we finished analyzing, but I think that it really does seem like we've been able to entangle the two systems. I guess I can say that so far. And then this then lets us go ahead and say, well, how can we think about making that more efficient? How can we make that better? How do we characterize the states of these remote two systems? Right, so that's where we are right now, kind of working hard at generating and characterizing entanglement between ions in two remote traps. And then in the last few slides here, I just want to show you how we want to kind of go beyond that, not only by increasing the fidelity and efficiency of a 2-node network, but moving towards a 3-node network. So now I've added a third picture in the upper right-hand corner. This is another kind of ion trap. It's actually one of the ones I showed you at the very beginning of the talk. It's a so-called wheel trap that was developed by the NIST Boulder research group. And so we realized that it would work very well for integration with an optical cavity, and in particular with an optical cavity based on optical fiber. So this is now a much, much smaller cavity. The one I showed you earlier, the one in the upper left corner, is about 2 centimeters apart. In the lower corner, this new one, this fiber-based ion cavity system. So it's 2 different images. One is the photograph in the upper right, in the lower left is the schematic. And so you should picture the trap, and then on we have these little optical fibers, and on the end of each fiber is a highly reflective mirror. So it's also a cavity, but now these mirrors are only about 500 microns apart from each other. And that should allow us to really boost the coupling strength, the coherent coupling strength between the ions and the single photons, and hopefully then thereby suppressing the role of spontaneous emission. So right, we first trapped ions within these fiber mirrors about a year and a half ago. We took some preliminary data on coupling ions to these cavities. And again, it's an ongoing project to try to see if we can get this kind of coupling between ions to cavities also working with this fiber-based system. Something that I won't have time to talk about today, but that we've recently put on the archive is work where we've analyzed the role of the dielectrics of having these fiber mirrors so close to the ion trap, and whether that is compromising the computational ability, essentially whether that's heating up the ion, which could lead to infidelity in the gate operations. So we're very interested from this technical point of view about the cavity, to the extent to which the cavity might disturb the ion trap potential. And so we're trying to find ways to build a system where we can couple the light from the ions to a cavity, but not also limit the ion trap computational abilities. Right. This is what I mentioned here, this understanding the role of dielectric in ion trap heating rates. And we've just wrapped this up recently and put it on the archive. And then we have also recently, or a couple of years ago now, we proposed how to use microelectromechanical systems to manipulate these fibers and couple them to the kind of surface traps I showed you earlier. So this is kind of a new idea for how we could maybe integrate these kind of optical fibers with an ion trap, and it's something we're just starting to test in the lab. We've just started a new project to try to assemble and test this kind of system this year. Right, so it brings me back to the question I asked at the beginning: how can we connect different kinds of quantum systems? And what I've focused on today in particular is ions in different distant cavities. So the ions are, of course, the same system, but the connection is via photons. So we're relying here on a hybrid ion-photon quantum system, and that's mediated by an optical cavity, which is allowing us to collect photons with high efficiency, but also it's fundamentally based on a coherent process. That is, this coherent interaction between the electric dipole of the ion and the field of an optical cavity, the vacuum field. So to summarize what I've told you today, these kind of quantum interfaces allow us, broadly speaking, to build links between disparate experimental platforms. And the trapped ions that I've highlighted for you are among the several leading candidates for nodes of a future quantum network. So I think that we're very excited about the potential for ions, but here I also want to highlight that it's quite likely that such a network will be made up of different kinds of systems, and the links in a network will have to bridge the gap between different kinds of quantum systems via photons, but probably also then via converting photon frequencies to different frequencies. And then the most recent experimental result along these lines that I highlighted for you was the Hong-Mandel interference that demonstrates this indistinguishability of photons that are entangled with remote ions. And then we're working now on using that as a building block for remote ion entanglement. And that's the data that we're taking now in the laboratory. So thank you very much. Let me show you my group that's been working very hard on these questions. And also I want to highlight Ben Lenian's team at ICOCI. This is at the Institute for Quantum Optics and Quantum Information, the other ion trap that I showed you here, and also theory work by Nicolas Sanguard's group. Thanks again.
Thank you very much for this very well structured and great talk, Tracy. And actually on the Discord channel, when you started, I just put up your homepage or the group's homepage, and that picture is there. So. Oh yeah. Okay, so we have actually a couple of questions, and of course, people are saying also that this is a great talk on the chat channel. Let me start with the question in a chronological order. So the first question is from Florian Ginzel. Let me read it. In the remote entangling experiment presented on slide 19, so perhaps we should go there. How important is the timing of arrival times of the photons at the beam splitter?
Can you say that again, the last part?
Yeah, so how important is the timing of arrival times of the photons at the beam splitter?
Right. So yeah, we talked about the photons being coincident, but it actually, I mean, there will be a gap. It doesn't, sure. It doesn't mean that they're going to arrive at a time you can't distinguish. And the question is, does that time gap tell you anything about which one came from which ion? Because as soon as it does, then you have a problem. So that's how it's important. And so, right, in this case, as long as you got your timing right and you excited them at the same time, and so the probability for the photon arrival is really overlapping perfectly, then you should get no information about those time delays. And so then it shouldn't matter. If for some reason you had, there's like an offset, maybe one cable is longer or one laser came on at a different time, then that would maybe compromise the entanglement.
Thanks a lot for this answer. So the next question is that from Devdut Sharma. Can we use soliton wave for quantum information technology? Did any research group use till now the soliton wave? I guess, I don't know if you need clarification of this question, perhaps.
Yeah, there's nothing that comes to my mind right away, but maybe there's something that helps to clarify.
Yeah, actually, yes. I mean, we have a couple of questions. So, Dev, if you want to clarify, please write it in the chat. So then there are couple of technical questions and then some general questions. So some technical questions from Vsevolod Shalakhdinov is the following. Does the lenses inserted into a vacuum chambers have indium tin oxide coating to reduce ghost charging?
What was the first part?
The lenses inserted.
The lenses.
Lenses
yeah.
inserted into the vacuum chambers have ITO, indium tin oxide coating,
so
to reduce ghost charging.
Yeah, in this case they don't. I think we're not too worried because they're so far away from the lasers that we're using, and in particular from the trap potential. So they're far enough away that we wouldn't worry about it. But certainly ITO would be something you could think about for optics that were closer. Unfortunately, for cavity mirrors, it would compromise the reflectivity too much. But for lenses, you could think about it potentially.
Okay, thanks. So he has another question also. Could you please explain the reason of getting entanglement with simultaneous Raman excitation? And he continues, you said it is because of coherent excitation, but then how did you achieve that coherent excitation?
Right, so let me maybe go back to this Raman process. So I think that I mentioned kind of some of the strengths of it here. So so the reason I would say that one reason to do it coherently is because if you use spontaneous emission, then the amplitude and the phase of your entangled state will be fixed by your Klebsch-Gordon coefficients. And so you're going to get one particular entangled state, and that may or may not be the one you want. And you should, maybe you'll look around and choose your states, choose the particular states that you use to get you the one that you want. But here we have the freedom to tune our entangled state by tuning the amplitude and phase and relative phase of our Raman field. So that gives us a lot more control over the process, I would argue.
Okay, thanks a lot. I think it was a very clear answer. So then there is a more generic question from Kiran. How can we investigate the effect of inevitable loss and noise in quantum channels? So let's say with your apparatus, I guess, like in a channel when you transmit, let's say, photons between, or you have a electromagnetic transmission between two cavities. I'm trying to interpret the question.
Yeah, thanks for the interpretation, and I think it's a great question because first of all, it's very fundamental, right? We want to understand these quantum systems coupled to the environment, and also, of course, it has a role for quantum technology. So I think I would describe our investigation of it is in terms of this comparison of experiment and theory. And for us, these kind of theory calculations that we do. So for example, here, when we look at these kind of coherent, these wave packets, the temporal wave packets of the photons, what this is a master equation. So it's integrating the master equation that describes the interaction of the ion and the photon, including the dissipation channels. And so we do that with, previously we did it with MATLAB. These days we do it with QTIP and Python. And so if we see the kind of agreement that you see here, we feel confident that we really understand the behavior of our system, so we really understand the role that the environment is playing. And then that lets us make these kind of comparisons that I showed you in this plot here, where then we can kind of partition in the dotted and solid lines in the lower plot. You see the difference between sort of the ideal case without the interaction with spontaneous emission, without the noise from spontaneous emission or the loss, and then the role of spontaneous emission. So I think, yeah, I would say the key is the comparison with theory, and then if we can trust that the theory is capturing our experimental data, we can then go back to that master equation description and understand the role of the environment.
Right. Yes. By the way, do you think you can even capture, because you are talking about like a master equation, so it's usually then you are working in the Markovian limit. So do you think you can capture even non-Markovian effects?
So yeah, it's certainly, I could imagine that. I think that there's interesting ideas there. I think we don't have any concrete experiments planned, but I could imagine that, yeah, you could write down, you could, yeah, it would be a question of writing down those effects and being able to model them, and
yes.
And providing, and yeah, kind of coming up with those special channels that aren't just dissipation, but are feeding back.
Exactly. Okay, thanks a lot. There is a question from András Pályi. You showed this 3-trap setup, and he asked, which experiments, applications are you aiming with that setup?
Yeah, so this is also something that we're very much engaged in right now, and this Quantum Internet Alliance that I mentioned at the beginning, something that's exciting about that collaboration for me is that it involves us with a lot of theorists. So for example, people like Alam Kashefi in Paris, or Anders Sorensen, or Stephanie Vayner's group in Delft, who are thinking about questions about, what are the protocols we want to do, and can we analyze what the kind of simplest network demonstrations are. So, what you can start by, once you demonstrate this kind of a link, you start by doing things like, say, teleporting states. And then maybe what you want to do for a network application is look at something like blind quantum computing, to say, imagine that one of your systems is a client that has a computation that it wants to run, or that he or she wants to run on a quantum computer, and is trying to send that information to a quantum computer without the computer knowing the problem. So there's been a blind quantum computing demonstrations with photons, but it might be really nice to show this in a network-based, so in a matter-based qubit setting in a network, I think. And yeah. Go ahead.
Yes. So this is a nice. Sorry, maybe I interrupted you.
I think that was what I was saying, that as an example of an application would be a blind quantum computing protocol, and then you could think, that's something you could test with 2 nodes, but then you could extend it to multiple users with 3 nodes, for example.
Exactly. So actually, since András is a close collaborator of mine, and actually in this session, at the end of this session, in 1 hour from now, there will be a talk where we are both involved. I mean, I think what he had in mind is that there is an interesting quantum communication protocol, the Byzantine agreement, and actually also in the quantum case, with 3 nodes, you can perhaps even show that. So that would be also perhaps an application. There is a very interesting question from Joel. Intriguing, I would say more. Besides photons, is there any other candidate to send quantum systems from one point to another point?
Yeah, so I think it's intriguing, because it also kind of forces you back to the question about, why did we get excited about photons, right? And we like photons for fast transmission over long distances. But you might say, well, actually there are circumstances where you maybe don't care about the long distance. Like maybe you want to build a superconducting quantum computer, and you want to, have a distributed computer where it's, but these are very close together spatially, right? And so maybe you could use, phonons instead of photons there over short distances to make links, for example. So I think also, there have there was an interesting proposal some years ago about using very long storage times in solid state systems. So in some of these solid state systems, there have been actually quantum memory storage times for several hours that have been demonstrated. So you could imagine on the timescale of several hours, if what was interesting to you was transporting quantum states, you could actually sort of physically carry those, right? Write them into some kind of a solid state system and transport it with a car or a train or a plane. So people have thought about those things, absolutely.
Thanks a lot, and thanks a lot for all these answers. I think it was really great. Also, these questions and answers, and I would also like to thank those who posed questions. There is a couple of more questions, but unfortunately, we don't have time. But on Discord, perhaps you can post them also on Discord. And Tracy, if you have time, maybe look at your Discord channel. Also, there was a final question about whether you could share your slides on Discord, or we could put them on Discord if you have if that's okay for you.
Yeah, so I forgot to log into Discord before the talk, but after the talk, I'll log in and also save my slides as a PDF, and I can put them there as well.
Perfect. Yeah. Thank you very much. Thank you.
You're welcome.